So if there are no questions, then, I mean, it looks like everything is clear. We are going to continue from where we left off yesterday. I was hoping we could sort this thing out, right? Normally what we do in this course is we usually have 2 class reps, a male and a female, just in case there are people that feel comfortable chatting to a person of the same sex. So, can we get this out of the way? Volunteers, who is interested in becoming class rep? 1 female, 1 male. Sorry, your name? Sorry, last name? Monga. Your name? Excuse me. You keep quiet. If you're interested in becoming class rep, raise up your hand, and then we're going around in circles. Chileshewu? Your name? Oh, your name? Chilufye Chanda. Your name? Francis who? I don't know if this is, I heard you right. Your name? Is there anyone else? Without an A? Is there anyone else interested? Your name? George who? Sorry? Smangolwe? Okay. Your name? Chanda who? Is there anyone else interested? No. Okay. Okay, so we'll go around in circles. We'll start with Thelma in less than a minute. I guess in 30 seconds, we don't want to lose time. In less than 20 seconds, do you want to tell the class why you want to be class rep? So you're going to have to vote, so you want to pay attention to what they're going to say, right? Just anything.
Hi, my name is Thelma Wonga. I volunteer to be a class rep because I'm efficient and I'm super friendly. So I'll be on time with information that you need to know about the course, and I'll be there, I'll be of service whenever you needed me to. So it's more like a micro with age and everything. So yeah, that's pretty much it.
Okay, thank you. Excuse me, could you Chilufwa? Oh. Chilufya, Miss Chanda, do you want to tell everybody why you want to be class rep? Hi. Hi. Yes. Miss Spirit, do you want to tell the class why you want to be classroom?
I'll try next time.
Miss Sanga, do you want to, shh, please. Do you want to stand up and tell everybody why you want to be classroom?
Okay, why I want to be this is actually pretty great. I want to say I have great communication skills, but I want to help everyone come to class on time. Everyone to understand and be, told about everything that's going on in this class. That's all.
Shlesha, do you want to tell everybody why you want to be classroom?
Okay, guys, I'm willing to be a class rep because, I want to work with you guys. I want to help you. I want to give you information, where
Excuse me, give him a chance to speak, right? What's wrong with you?
where possible, and one person was fair, I don't segregate. I'm fair to everyone, and that's all.
Okay, thanks. Francis, do you want to?
I want to be a class report. I don't know, I just have so much stuff on this side. Wow. I feel like and sharing information with you guys.
Okay, thanks. George, do you want to?
I'm a straightforward guy. I take the suggesting, so I think I will be of help to you.
Okay, so could the six of you just quickly dash outside and just give us time? No. So I'm assuming people were keeping markers, right? Signals of who they want. So start with the females. Those that would want, please don't make noise. Those that would want Miss Monga to be the class rep, raise up your hands. That's one, two. Also, you're only going to vote once, right? So just once. 1, 2. So by my count, those that would want Miss Shanda to be the class rep, raise up your hands. 2. Miss Sanga. Okay. Those in favor for Kamfwa. 3? Okay. Oh, okay. Oh, those in favor for Francis? Now, I'm wondering what, I mean, is different factions or something, I don't know. Nobody voted from here. Those in favor for George? Excuse me. 1, 2. Come on, man, don't act up. I counted 14. I hope there was someone. Excuse me. So it goes without saying then that. No, I'm not rigging the elections here. I mean, I want people saying that Kagai did that, Thank you so much. Come in. So the class reps are careful with the cable, right? All right, so it appears, so the vast majority of people, thank you for volunteering, by the way, I'm really grateful. So Thelma and Francis, could you stick around after class so that, I suppose I give you my contact details because there are a couple of things that we need to sort out. All right, so if there are no questions with regards to the course syllabus, now would be a good time for us to continue off from where we left off yesterday. Specifically, what I want us to do today is to have a broad overview of what the course is all about, right? I mean, as far as the administration and management of the course is concerned, I'm sure people are familiar with what goes on, and the things that I want to specifically point out are things related to the grading system, and more importantly for me, this whole notion of academic dishonesty, right? You want to stay away from that. So it turns out that the things we're doing in this course are pretty straightforward, right? I mean, the broad learning outcomes for the course, I mean, everything we are going to cover up until somewhere is it in October and November, is centered around these broad learning outcomes or objectives, right? So by the end of the course, hopefully everybody who is enrolled into the course is going to be able to identify the different types of computing machines, right? And also I should mention here that you realize that some of these objectives will actually pop up in different themes and topics as we discuss them, right? So it doesn't necessarily mean that this objective is exclusively tied to a particular topic, no, right? If anything, most of the things that we're going to be discussing are actually interlinked together, and I'll explain more just now. So we should be able to distinguish the various components of the von Neumann architecture, and this thing will come up once we discuss the core functional units of this thing we call a computer system, right? And then we should be able to explain in great depth how these computing machines, things we're calling computer systems, are organized internally. And then explain the various design trade-offs between different computing machines. There's a lecture dedicated to classification of computer systems, and I think this objective actually stems from that particular theme or topic. And then we should be able to describe exactly how a computer performs calculations, right? It turns out that everything we do on these things we're calling computer systems, whether it's your phone or if it's my laptop, could be anything, the computer actually gets to interpret the input we pass to it in a certain way, right? And behind the scenes is very basic arithmetic operations that actually take place, right? So we want to be able to understand exactly how these calculations are performed, which explains why we're going to spend quite a bit of time looking at number systems, right? Revision, I know for most of us. And then we should be able to explain exactly how bits and bytes, fundamental units used to interpret, to represent data in the computer, are organized, right? In order for this data that we kind of want a computer to process, in order for us to understand how this data we pass to a computer is processed. A lot of this will come out, let me see, I think once we start discussing the MIPS instruction set architecture, and also once we look at data encoding, right? So we'll get to a stage where we'll explain exactly how sound is encoded, right? So what actually goes on when Lighton is speaking, and the voice or the sound is, obviously it has to be converted in the form that a computer understands, right? So what happens and how is this information stored on a computer, right? And that's important because you want to be able to retrieve the things that are saved, right? So once you retrieve them, how exactly are they converted back to a form that human beings can understand, right? Essentially, what we are doing is passing input to a computer into a form that it understands, and then once it does the processing, it spits out an output that end users, aka, for the most part, human beings are able to understand, right? So it's a really interesting course, a very fundamental course. If you are remotely interested in computing, various aspects of computing, actually, I would really encourage you to pay attention to this, right? There's some things that we're not really going to cover, like advanced concepts that are linked to this, you know. And really, you probably realize once you start looking for resources online that we're just scratching on the surface, right? Some of the things we're discussing, things we've classified as topics and themes are actually full-fledged courses elsewhere, right? So for instance, we only get to discuss operating systems when you look at computer software, right? But I remember when I was a student myself, there was a dedicated course aimed at studying how operating systems actually work, right? I think it was a year-long course, right? Still, when you're discussing computer software, we'll look at these categories of computer systems called the language translators. I did a course on compilers, right? A compiler is essentially nothing more than, I guess, a type of language translator, right? So exciting stuff going on here, but takeaway point from this slide is that fundamentally, we're going to cover, our goal is to actually ensure that everybody gets to work towards these learning objectives. Okay, and also, this, you see this, you probably grow tired of this. This is going to come up over and over again because it needs to sink in, right? The definition of what a computer is. It's nothing more than an electronic device that accepts input, you know, so you feed the computer input. I don't think we've started classes yet, but hey. It's nice, right? But it's always nice to write. Apparently, right, I read somewhere, and I think people have done research in this, I don't know. Apparently, you're able to effectively retain information if you write things down rather than just read. I don't know how that works, but I don't know if it's true, but I remember reading about it. But anyway, so in trying to work towards these objectives, really, we want to understand what goes on when we say a computer is an electronic device. A computer system is an electronic device that accepts input, processes the input, and then presents the changed input as output. Right, so fundamentally, irrespective of the type of computer you might think about, it does three key things. It accepts input, right? It processes the input and then provides output. So everything, you know, laptop, mobile devices, right? The traffic lights. We can go on and talk about a whole bunch of things. Facebook, right? Facebook, you know, is not a computer system; it's a software application. But I suppose the machines that host Facebook, I suppose. Right, so we are wanting to really work towards understanding exactly how this computer interprets the data once you feed it with the input, right? What goes on behind the scenes, what sort of processing goes on, and how exactly does it represent the data that it produces as output, right? Because it's not always the case that the output is going to be consumed by an end user, right? There are certain instances when the output is probably going to be saved somewhere, right? So how exactly is that saved output represented? Exciting stuff, guys, I assure you. So essentially, right, and I always have to explain why we've taken this approach, right? So we this last couple of years, I guess 2 years since I started teaching this course, we decided to take a top-down approach in trying to, you know, work towards the different themes and topics in the course, right? So the idea is to explore the high-level, you know, components associated with the computer system, and then get to go down to the gory details, right, the specifics. And we'll predominantly do this by taking advantage of this whole notion of abstraction. It's a dedicated lecture series, short lecture series, to explain what abstraction is all about. We shall also give examples of abstraction in computing, because it turns out that it's not only applicable to understanding this computer, but when you do 2010, it will come up as you're learning how to program in Java, right? Abstract classes and things of that nature. It turns out that there are people elsewhere that prefer to take a bottom-up approach, where I guess you view it as a first principles approach. So you start by looking at the specific details associated with how a computer works, and then you work your way up, right? So you probably start with logic gates, and then you go to see how exactly this thing we are calling the instruction set architecture gets to function, and then all the way up to the high-level functional units, right? Input, output, the various components that make up a computer system. But I think that we've done quite well in taking a high-level, a top-down approach, without even really bothered to find out from people that have done the course before, whether this approach is effective. Now, I don't know what the best way would be, right? Because for you to be able to ask someone if an approach is effective, if this approach is more effective than this one, they'll have to have experienced both approaches, right? But maybe next year we can take advantage of the bottom-up approach and then figure out how to extract, information from you guys and then extract information from those people. Or perhaps we can say, let's see how many people passed using this approach, and then, but I know, right? I don't know. Okay. Right, so in trying to work towards these really broad objectives, the order of like topics and themes we're going to cover as follows. Beginning Saturday, I think, we shall start our discussion of, we'll look at major historical milestones that have taken place since the 1940s, mid-1940s, all the way up to now, right? And it turns out that the milestones can best be understood by looking at the different, we call them different computer generations in between 1945 and now, right? Turns out there are 5 generations, so we'll look at them in great detail, focusing on technological interventions that, were more specific to those particular generations. So in computer generation number 1, what was the more prominent technological intervention, right? In computer generation number 5, what's there, right? But what we also do really is to look at some other devices that were invented prior to 1945 that are still considered computer systems, because it turns out that they have certain things in common with modern day computer systems. And fundamentally, really, they accepted input. I don't know if they process, some of them process the input and then presented output, right? So computer system. And then we'll try and really look at the different categories of computer systems, because it turns out that these things we're calling computer systems come in different shapes, right, and sizes. They have different functionalities. A computer system that is supposed to be used for things like traffic light, for instance, is different from a laptop that Lighton is using. The computer system that is used to run that point of sale machine when you go and buy things in, I don't know if you go to ShopRite or Pick and Pay or whatever, that computer system that the teller uses to, scan things, the barcode on the products that you want to purchase and whatnot, it's different, right? In certain instances, you notice that some computer systems are specialized. They do one specific thing. Some of them are generic, right? I can watch movies here, I can project a presentation, I can type, I can program using this, so this is like generic, right? It's general purpose. So we'll look at all these different classifications, and it turns out that the different classes are best perceived from these core categories here. So we'll look at these things they call embedded systems, embedded computer systems, microcomputers, mini computer servers, mainframes, and supercomputers, right? Although we will mention the fact that, we'll mention the fact that there are some categories that are more or less like obsolete. Like these days, there are only very few places that make use of mainframes. Right? But we'll discuss them nonetheless to look at the comparative advantages and disadvantages, what sets them apart from the other categories, right? And more importantly, we want to understand in what sort of usage setting would want to use either one of the categories. So when would you want to use an embedded computer system, for instance? I don't know, printer or something like that. I have Arduinos. Anyone know what this is, right? Yeah? Zesco. Yeah. Sorry?
It's a meter.
I don't know. But it's much more than a meter, right? It's much more than a meter. What this thing does, right? I'll bring it, I guess, on Saturday. This is courtesy of me. It's called, Zesco calls it a customer interface unit, and what it does is it accepts input by way of, if you want to recharge, right? You buy a token and then you key in the token, you recharge. Sorry? Oh, sorry. We'll go back here. I'm saying it accepts input, it processes the input and then provides output. But it's an embedded system. It's also specialized. It can't do anything other than just recharge and show you how many units you have left. That's it. Can't use it. And it turns out it has certain specific features that enable us to classify it as an embedded computer system. Exciting stuff. And then, once we are done with defining the broad categories of computer system, this is really a topic that we historically used to cover in the second term, but I think it's important that we look at it in the first term. This whole notion of abstraction, so that we really appreciate how useful and how valuable abstraction really is, right? It turns out that most of what we are doing is can be looked at as, or can be classified into 3 layers of abstraction, right? So we look at the software component, we look at the instruction set architecture, right? Software enables us to communicate to the computer system, right? Because we can't directly fidget around with the hardware, so software enables us to do that. But also, we don't directly interact with the hardware using the application software tools. We have to go through the operating system. So web processor, when I'm typing, or when I'm creating slides or something using PowerPoint, if it's Microsoft PowerPoint, whatever it is I'm doing has to go through the operating system, and then the operating system gets to interact with the hardware, right? But there's a lot of things going on behind the scenes, right? The instructions that were used to create the different applications that we have to be interpreted in a certain way, right? So it's where the instruction set architecture comes into play. We have a number of dedicated lecture series for the instruction set architecture. Probably 4 lecture series for this or something, maybe more this time around. No, actually, slightly more than 4. So layer number 1 is the software, and then the instruction set architecture, and then the hardware. Right, on the hardware, we're essentially just going to focus on the high-level functional units, and then towards the end of term 2, we'll look at logic gates, right? So I guess that falls under circuit design, right? It's hard for people to understand or appreciate the fact that fundamentally, you know what they say about a computer does what? It works with ones and zeros, right? Electric signals. So we want to understand exactly how those ones and zeros get to be translated from here all the way up to the point in time when you're sending through those pulses, right? High voltage and low voltage. So it's really important topic really to help you understand the other things that we're going to discuss. Also, right, some of the things that we'll probably discuss in term 1, we will revisit in term 2. So there's nothing like what we cover now won't be useful then. Everything is connected. And then we will jump on to look at, we have, I think this time around we should focus more on computer software. I think the mistake we've made in the past is not really focusing more on the operating system. So we'll do that. We'll probably have a dedicated lecture series for that. But as we're discussing computer software, we'll look at the different categories of software, you know, why do we need computer software, right? Different classifications of computer software. It turns out that there are different categories, right? These things I was talking about, like language translators, operating system software, application software, firmware, and all these funny things. We want to understand and appreciate when and how we should use all these different broad categories. Be able to cite examples, right? Why, you ask, right? It turns out that one of the things you're going to be taught in second year is how to write software. Before you can learn how to write software, you want to understand how software functions, right? But also, I think when you become a teacher like Lighton, you have to teach some of these things, right? So, go figure. And then, so we'll look at the classifications of software really we're going to look at is firmware can be classified as operating system software. So firmware, operating system software, language translators, utility software, and application software, right? And then it's almost always the case that when we're looking at different categories of things, we want to be able to distinguish one against the other, right? So look at the various differences also. One way of knowing that something is really important is if there are so many different people trying to come up with different versions of the same thing. Oh, I installed Windows, I installed Linux. Oh, I'm running Android on my phone, operating system software, right? It's an important thing because everybody is coming, there are probably hundreds of different types of operating system software, right? Some of them are specific to certain types of computer systems. Some of them are general purpose, like, I guess, the desktop version of Windows, right? Or Ubuntu in my case, general purpose, I can install it on a server infrastructure, I can install it on a desktop laptop like this one. I can actually even install it on a phone, right? In fact, Android is a Linux-like operating system, right? So the things that I can do on my machine here, I can do on Android as well. Most of them, actually, not all of them. But so, very important topic, I would pay attention. Actually, all of them are important topics, so I pay attention if I were you. And then we'll look at machine structure, right? I don't know why they call it, I don't know why we've called it machine structure, but I guess it's a code word for, it's essentially nothing more than the von Neumann architecture. Here is where we will discuss the high-level functional components that make up a computer system, a la the input, output, or input, output, the central processing unit, and the memory unit. These are the high-level components that make up a computer system, it turns out. That's all. And in fact, it might be hard to believe for some of us in here, but we'll spend the entire year trying to understand how the input-output component works, what goes on there, what goes on in the central processing unit. Everything we're doing is centered around these 1, 2, 3, 4 components. That's how easy this course is. We're just looking at 4 different things. Seriously. I mean, compare this with maths, right? What are you doing these days? Is it linear algebra or something? Or, I don't know, calculus, and I did that, and but it's nice though. And then after we look at the von Neumann architecture, right, we also look at the different other architectures that exist, but it turns out that most modern day machines are modeled using the von Neumann architecture, the von Neumann model, right? But doesn't mean there aren't other architectures out there. They're there, but not as popular as the von Neumann architecture, right? So we'll look at von Neumann architecture. It's really nice. And then after that, we'll actually start discussing these high-level components, functional units. So we'll start with the CPU. There's going to be a short intro to the CPU. Our focus is going to be on the so-called instruction cycle, right? So what is the role of the CPU, right? It turns out that the CPU is there to do nothing more than just execute instructions. The software that you use, or Microsoft Word, Ocular in my case, I don't know what other software, VLC and whatnot, turns out that all those different application software are composed of instructions. Those instructions are executed by the CPU. So we want to understand exactly how the CPU executes the instructions, right? This will come up again once we look at the data path and control, once we start our discussion of the instruction set architecture, because our discussion here will be at a high level. Once we start discussing the data path and control, the data path and control, we'll look at how the instructions are actually converted into so-called ones and zeros, essentially just high voltage and low voltage, and what happens, how does a computer get to interpret those different instructions, right? And when you understand this, you realize that this thing they call a computer is actually a very simple thing. Very simple thing, right? And then after the CPU mild introduction, the CPU will look at the input-output module or sub-module, right? We'll start our discussion with peripherals, right? So things like this laser pointer that Lighton is using, right? I shouldn't use this, I should probably use this laser pointer. Don't want to run out of time here. This laser pointer that Lighton is using, right? It's an input device. Why? Well, not the actual me pressing the laser pointer, right? But when I press the forward arrow and the back arrow, it turns out that the signal is being sent to that machine, right? This is an input device, an example of a peripheral, right? Another example of a peripheral. So I want to understand exactly how these things work, right? How they interface with the computer system. And then after our discussion of peripherals, it turns out that there are a slew of peripherals. And in fact, the way the computer is designed in such a way that you can invent a peripheral of your own, as long as you understand how the interface works, how this computer works. You can. You'll be able to do, we'll be able to interpret the input. This is how these people came up with this device, right? And all they do to interface this with the computer is you just plug in that USB thing, send the signal to the computer. And then we look at the I/O subsystem. So it turns out that these peripherals connect to the computer system or the CPU via this I/O subsystem. So we want to understand exactly how this is done. Are there any interesting techniques that are used? It turns out that they are, right? 3 key or popular techniques that are used. So we want to understand 4 actually. No, 3. Programmed I/O, interrupt driven, and direct memory access, right? So we want to see what the difference is between these different techniques or approaches. When is one used over the other? When is one more important, right? This is exciting stuff, ladies and gentlemen. And then we'll start looking at this other component, the memory unit, right? If you notice, I mentioned the central processing unit, input, output is combined into one. And then we'll transition and look at memory unit. We are spending quite a bit of time here because there are different types of memory components, right? These things they call main memory and whatnot. And, we'll look at metrics that are used to try and measure the performance of these memory components, right? We'll look at ways in which we can distinguish different types of memory components. When and where are these different main memory components used, right? So for instance, there are memory components on the CPU chip itself, right? So registers, for instance, CPU cache sits on the CPU. There's this thing they call RAM. There's ROM, right? So this thing here, this thing here actually has ROM, right? It's read-only memory. Because it doesn't write any data anyway. Right. And then, so we'll look at the different types of memory components, right? This is really going to be exciting, I promise you. I think this is probably going to be the most exciting course, I assure you. Of all the courses you're going to, I promise you. It is. And then, before we start our discussion of secondary storage, which is essentially another type of, we're still discussing memory at this point, right? It's still another type of memory, right, but different type because it's persistent, right? So the dedicated lecture series for this. But before we start our discussion of secondary storage, we shall try and understand exactly how the output that we say the computer is produced, sometimes it's saved somewhere, right? How is it organized? It turns out that you store the data on secondary medium, right? So how is it organized? It's usually in the form of files, right? Files, folders, and all those things. So we have dedicated lecture series to look at file organization and file systems. And then we'll again start our lengthy discussion of secondary storage because it turns out that there are different types of secondary storage, right? Especially these days, right? Oh, my internal hard disk, and I bought a memory stick, right? I bought an external hard drive. I'm synchronizing my work to cloud storage. I'm using Dropbox. I'm using Google Drive cloud storage. Right? Those are all different types of secondary storage. And we have an in-depth discussion to appreciate why they're important, when you want to use them, right? And a number of interesting things will come up. Things like aspects like cost, size, performance, right? Speed, effectiveness, how long your storage medium or storage device can actually store data, right? Because it turns out that you cannot store the data indefinitely on some of these storage devices. Like a lifespan for some SSD storage, they'll say is maybe less than 5 years or something, I don't know, right? And maybe this would be the best time for us to talk about some of these interesting things that people are working towards. I was watching an interesting, was that a documentary or something the other day? They were saying they're experimenting with storing data on special purpose glass, right? And they promise that this data can persist there for millions of years, right? Interesting things going on here. Especially now that we're generating massive amounts of data, right? People are probably WhatsApping here, that data is being stored somewhere, right? Hopefully you're backing it up somewhere. People are going to go on Instagram and see what people are up to, right? Post things on Instagram. That data has to be stored somewhere, right? So we will really, this is very important, like everything, exciting topic, I guess. So for some of these topics we're going to cover, right, unfortunately, there are no dedicated courses, right? For things like computer software, there's a dedicated course, 2 courses actually, where you're taught how to write computer software, right? So it's coming back. But for some of these things, you want to pay attention because it's the only time we're going to discuss them, right? And then, so everything I've discussed so far is in term 1, right? This is hopefully by the time we get to, is it May or June or something, would have finished with topic 11, right? I don't know if, right, so by the time we get to, where are we? By the time we get to 22nd May, we would have finished, the plan is to go up to topic number 11, so that we seamlessly transition into the computer architecture component in the second term, right? And I think we should be able to do this, assuming there won't be any confusion, usually confusion here. And then in term 2, we start our discussion of, remember the layers of abstraction I spoke about? We start our discussion of our instruction set architecture, and then there'll be a mild introduction of circuit design, logic gates. So we'll have a lengthy discussion. I think there are more than 20 lecture series dedicated to the instruction set architecture. We use MIPS because it's simple. There are a lot of resources obviously online. It's easy. It makes it a lot easier for you to understand the role of the instruction set architecture using MIPS, as opposed to something complex as x86 architecture, for instance, right? So we have a very small introduction to assembler or assembly language programming. We will use, obviously, we use MIPS, right? MIPS assembly language. This is what we're going to use, and this is where this simulator called QtSpring is going to come into play. A lot of hands-on stuff going on in the MIPS discussion, right? So we'll look at the architecture of MIPS itself, and then different types of instruction formats, right? So remember I said fundamentally what this computer does is it performs arithmetic operations, but at a very high level there are different types of instruction formats and they're interpreted differently, right? In fact, if you trace their path, they actually make use of different hardware components within the computer system itself. So we want to understand exactly how this addition and subtraction, multiplication, division actually gets to be translated into ones and zeros. It turns out that it's a lot easier for us to understand or to interpret the ones and zeros if we just go a level higher up, which is instruction set architecture. It's like when you're translating assembly language programs into ones and zeros, it's almost like a one-to-one translation, actually. And we're going to do that translation at some stage. Because when you're writing programs using a high-level programming language, you tend to use very basic constructs like loops and conditional statements like ifs and whatnot. We want to understand how all those things are interpreted, which is why we have dedicated lecture series to look at those constructs, right? So looping, how exactly is looping done using assembly language program, functions, how do we get to move data, right? From main memory into sending it to the CPU, for instance, right? Because the CPU wakes up, listen, the thing we call a computer, right? All it's doing is, think about this for a second, and we'll think about it some more. But you want it to do something for you, something that you know will take a long time. It does it just within a split second in certain instances, right? So, but the computation, the processing takes place on the CPU, right? And what you're processing is data, right? That data normally sits somewhere, it's usually secondary storage and moves to main memory, and then from main memory, the CPU actually fetches the data using the instructions, right? So we'll look at how this data is moved around as well. And then we have, before we can start our discussion of data encoding, we have a revision from grade 5, number systems. We did that, base 10, right? Remember that? We're going to do that, whether it's this time around, I don't know if you did base. We're going to look at hexadecimal, which is binary and decimal, right? And the reason why you shouldn't see why we're doing this, decimal because human beings understand base 10 better, hexadecimal because it's a lot easier for you to understand binary, which is the ones and zeros using hexadecimal. It's much more intuitive because all you're using are these characters here, 1 up to 9 and then A up to F, right? And then we'll look at ones and zeros of binary because the computer gets to store these or interpret instructions and everything else in binary, right? So 1 to understand is 2, binary. And then after that, we have yet another dedicated lecture series where we look at how data is represented. Think about this for a second. The thing we call data, the things we input to a computer, it's sound, it's text, it's images, it's video, it's colors. I mean, so some of them are composites actually, like a video is a composite of an image and sound. But so we want to understand exactly how this is encoded into ones, because we're saying a computer interprets all of this using ones and zeros. So how exactly is sound represented using ones and zeros? How are images represented using ones and zeros? How is video represented using ones and how are colors represented using ones and zeros, right? Really, probably, I guess, we didn't do a poll, but I could sense people were really excited about this course because unlike some other topics that are more abstract, that require a bit of thinking, you can easily relate to most of these things, right? When we look at these different types of data formats. I mean, you use them every day, right? Not a day goes by without you posting something, a picture, perhaps selfie, don't know, right? Or reading the news or something. And then after our discussion of data encoding, we transition to the data path and control. Again, still MIPS, because it's tied to the MIPS instruction set, which is, I think, topic number 12 or 13 or something. So to essentially appreciate and understand how the assembly language instructions, how exactly are they converted into ones and zeros, right? So we'll be able to understand what this is, actually, once we get to this stage. And also, by the way, again, it's not like we're abstracting things here, right? It's not like they're ones and zeros. These are like electric signals, right? So 0 for no electricity or low voltage, and then 1 for high voltage or electricity or something. This is how a computer works. It's just electricity, right? And then finally, I guess the last layer of abstraction, we get to look at logic structures. Because for a computer to work, you need like these high-level components that help you process these ones and zeros, right? Fundamentally, right? So we'll look at I think you've done this before, the AND gates and OR gates and whatnot. So we'll look at this very simple topic, actually. And I know the way the course is designed is we just gloss over the surface, but I always feel like it's important for us to look at how certain core hardware components are implemented using gates, right? So for instance, the component that does your adding in a computer, right? The adder, how exactly can you construct it using these fundamental gates or logic gates? The register, for instance, right? So, yeah. And so I went home and I was looking at the kind of compressed everything into themes, and I was counting the number of hours we spent on these different themes last year. And it turns out that these are the corresponding hours. You notice that there are certain topics where we spend a lot of time. Like you can view an hour as being like one lecture series or something, right? Or one session like this one. So you notice that we spend a great deal of time on computer software, quite a bit of time on computer memory, right? Because computer memory is composed of main memory storage and what files or file organization and file systems. And these are the high-level functional units like the central processing unit, the I/O subsystem peripherals, and the I/O subsystem itself is a combination of both of them. No, this is not 1 hour. It can't be 1 hour. Mistake. It needs to be fixed. I don't know why I made this mistake or how I made this mistake. Must have been making some changes here. But doesn't matter anyway. Well, I mean, so I know where that is coming from. The way this works, right, is there's no marks for attendance. If you want to walk out, door is always open. Sometimes it's closed, but you can walk out and leave. But in case you were wondering, I don't know what goes on in high school, whether you have to do may I leave the room or something. But it doesn't work like that, at least for this course, right? I don't mind if you walk in and then 5 minutes later leave, if you're rushing for it. Listen, there are a number of things going on. There are times when you need to go to another class that's perhaps in vet or something. So for you to go there, you need to go there in good time. You're welcome to leave and go. Maybe you want to catch a bus, you're welcome to leave and go. So these are approximate number of hours, but I'll update this, hope that's clear. I'll update this with the correct hours so that you have a sense of what we're going to be doing, right? The total though should be, because remember I said that it's not me actually. The terms, each term is allocated 15 weeks. And so if we have 3 lecture series each week, then what we are saying is that we'll have what? About 90 sessions, right? The total number of hours here add up to about 86, which is somewhat closer to 90, but the thing is we use some of the lecture sessions to write tests, you know, to do like recitals, and so it's a good enough approximation. So 86 is somewhat closer to thing. So in summary, really this is, well, again, a reminder that what we are doing is we're just essentially interested in studying how this thing we are calling a computer system, and it doesn't have to be this particular computer system. What I thought would be interesting this time around was, oh, did I forget that? What I thought would be interesting this time around was shift things around. I bought, I don't know if people have youngsters who use the WOW tablet. I think it would make a lot of sense if we tie everything to this tablet. It's an Android device, which means that we'll have to really focus more on Android and see how it works, right? I think it would be more interesting if we tie what we're going to be discussing to like a case or something. I don't know if this is going to work, but that's the goal, right? So it doesn't have to be this. It can be this. It can be your mobile phone, traffic lights, point of sale machine in ShopRite, right? These space probes are sending into space. Crazy things happening these days, right? So it doesn't matter what it is, but fundamentally they have certain things in common. This is what we're studying, what we're trying to study. So to quickly wrap up, because someone wanted to go, what's the time, right? Oh, I'll tell you what the time is. It's 18:01. But it's 18:01 because we ate up into the elections, right? It's not my fault, it's the elections. Ideally, it's on the dot after 45 minutes, we wrap up and then you have enough time to rush to wherever you want to go. That's the policy. But in closing, I do encourage you to attend all the classes for this course and for the other courses also. And all the tutorial sessions and the lab sessions, they are there for a reason. Think about this for a second. There's money being spent, right? Infrastructure, people being paid to do this. What does that mean? It is important. They've done this over and over again and realized that this is what works. At a bare minimum, if you attend all the lectures, if you attend all the tutorials and lab sessions, and if you study, you will pass this with flying colors and any other course. I promise. If I were, I know it can be tempting, you know, I won't attend the course. I will go to the quiz, but then you go out and you party, you get drunk and you oversleep, you miss a quiz, and like it's fine. I would refrain from doing that if I were you, right? You want to sit for all the assessment. Every mark counts, I promise. Every mark counts. I think you saw that snapshot where I was showing you the grades, right, for some of the students from last year. And also, I'd encourage you to actually participate in the various other activities that take place. Ask questions. You know, there are forums in the Moodle. We have that course mailing list. It's as easy as just sending an email. Ask. And the tutor or Lighton will respond, or your other colleagues will respond. This is how we learn, right? In fact, this is one of the things that makes an environment such as this more effective. The support structures, the smart people that are sitting next to you, right? The diversity that is in here. This is always comes, if I were you, at least for this course, I don't know about what happens in these other courses, right? You don't want to cheat, to copy, to do anything, to plagiarize work. You don't want to do this because you automatically fail the course because you will get a 0 once you are caught in the CA. And writing the exam doesn't change a thing, right? Because you would have failed the CA. So if I were you, I'd just avoid any sort of academic dishonesty. This has been, I think this is probably the third time I'm mentioning this. It's in the course syllabus. What that says is that it's an important thing, something that you should really constantly, probably stick it up somewhere in your room, right? Yes. The thing with academic dishonesty, to remind yourself before you leave your bedroom or room or level or something, to say, oh, academic dishonesty. And it doesn't just apply, it's bad to cheat, right? Yes. The reason why this has become so pervasive is The same reason why corruption is rampant elsewhere, right? Out there in the Republic or something. I don't know if there are any questions, guys, about really the rundown of what we're going to be doing up until somewhere around October or November or something. Any questions, concerns, comments? Yes?
What is NIPS?
NIPS is just a type of instruction set architecture. So the thing is, you see, each type of, well, I guess anyway, this is just instruction set architecture, right? Yes?
You said assessments and quizzes will be posted in the Moodle.
Yes.
Right? Then from the Moodle, they have to be copied or printed out?
No, you submit using the Moodle and then everything is electronic. And you should be grateful because you don't have to spend money going to print things out, right? So there's usually an automated submission process to workflow using the Moodle. So, of course, I mean, so this doesn't apply to class theory tests because you have to come physically here and write the test, right? So meaning, write it using a hard copy or something. In certain courses, I guess there are like practical sessions where you get to do something on the computer. I don't know, I think in 2010 and EDU 1020, I'm told those things happen, right? So, so nothing like printing out. Any other questions? Or people want to go now? Yes? Yes?
It's showing quiz time.
17?
Quiz time.
Yes?
First quiz, here it is showing that it's on 20. But on quiz time it's showing in 1.
What is it showing there again, sorry?
First quiz is showing it will be on 20. But yet on quiz time.
Well, one thing I would encourage you to do is most of the things we are going to be doing in here are going to be moving targets. What that means is that things are constantly changing. I want to show you something quickly. Things are going to be constantly changing. So, as an example, I'm going to open up. What I noticed when I was creating this thing is I realized that the dates were messed up, right? It was like 2019 or 2020. So this is a revised thing. Yes, which date were you referring to?
That's 20.
Yes.
Yes, 20. But here it is written with 1.
Yeah, so this is the correct thing. So it's on the course web page actually. So 20th is going to be Thursday. Yes, so it's to be like this day, today, which is nice, right? I fixed this, so you want to get the authoritative source which is online. On that link I shared, yeah? You remember the link? You will find this updated thing. Notice the dates have changed somehow. But these are just tentative dates, right? Tentative, right? To give you an idea of what's coming. So yes. So we have is your question, do we have a quiz next, oh, it's next week, yeah. We have a quiz. How nice, right? I didn't notice that it was next week. Wow, oh, wow. No, but at some stage, you have to ease into what's going on, right? This is meant to give you a taste or a feel of what's going to be happening. And the sooner we start doing this, the better, right? Yes. So that you have an idea of what's coming. For when we are having quizzes, excuse me, come on. I'm not going to be like Miss Banda who is shushing, every time in class, right? I think this time around I'll be walking out, and assume that we've covered, come on, I mean, we are mature now, right? We are not in primary school. Doesn't mean that you shouldn't ask questions, but be mindful of the fact that there are people that are frantically trying to understand what's going on. Right? So if you make noise, you're disturbing them. Don't do that. It's rude. So yeah, so we have a quiz on Thursday next week. I'm really excited. Wow. Sorry? On the quiz?
Some of us have never done this thing before, so we have.
But we have started. We have a class on Saturday. We have a class on Wednesday. I'm confused here. Sorry? It's not my fault. This thing was, I'm not the one who creates a timetable, right? Everybody everybody's seen the timetable, right?
Yes.
When we have classes on Wednesdays, Thursdays, and Saturday.
Yes.
So I have a class on Saturday. And I just told you that probably a class would have covered historical milestones. On Wednesday, we'll probably cover classification of computer systems. So, are there any question?
What is the best one?
No, it's probably going to be the first topic, I guess. I'll send out a notification on what the first quiz is going to be about, on which topic, what we're going to cover. Usually though, right, you have a better sense of what the quiz is on once you've done at least 1 or 2 lecture series. So we'll see at what point we'll reach on Saturday and Wednesday, and then. Are there any other questions? Shh. Yes? Sorry? Oh, it's online, but I can, I don't know if, there are extras. Were there no extras? What are you doing with the extras? I thought you're supposed to give them back, right? Are there any other questions? Yes? Shh. Sorry? The link for what? There's no WhatsApp group, sorry? Oh, there's no, someone was asking about WhatsApp, there's no WhatsApp group, but what the other people have done in the past is they've created a WhatsApp group for the cause, right? For you people to share thoughts and ideas and complaints and whatnot. That has nothing to do with me, and I'm part of a number of WhatsApp groups. In fact, I've muted them. I don't do that. Why? For what? Why should I be a part of the WhatsApp group when we already have 2 modes of communication, right? There's a mailing list and there's Moodle. Why do I have to be a part of the WhatsApp group? Are there any other questions? No, I don't want to be a part of that. You need a platform where you can freely talk about certain things that you don't want to think like, oh, if Lighton knows about this, then I'll be penalized or something. So at least that thing is yours if you want to do that. Some people, I know I've told elsewhere, people have preferred to use Facebook groups, private groups, whatever works for you, right? But for this course, what we think has worked in the past are using the Moodle and the course mailing list. Why? We have a historical record of what's going on forever. Are there any other questions? Yes? Yeah, so that thing, I'm not sure if everybody has been, I don't know if people in here, if there's anyone whose email account has been created, the ones assigned email. If not, then I'm sure with time it should be. Student number at student.unza.zm. So the thing with the mailing list is you can only access it using your official UNZA email account, which is assigned to you. So that's why remember I mentioned that there will be a training session that's to do with Moodle. It's also linked to the same email thing, right? So they'll probably show you exactly how to access it in due course. But for now, I mentioned last time that everything that you need is going to be available on the course, official course webpage, right? This. You'll find these notes, you'll find the syllabus and everything else. But what are you doing? It's in there. Guys, if there's no... yeah, but it's in the document, right? Guys, if... oh, yes. Shh.
Yesterday showed that 3 books that we should get notes from. So which one?
I didn't say you should get... I said most of the concepts we're going to cover I discussed in those books. But I also said that at the end of each lecture, there will be a link there'll be links that will be provided to alternative sources of the same information. But if you want a book, if you want books, because people are usually obsessed with books, I said you can go with those books. Yes?
That link is not...
Sorry?
That link is not...
It is there. You want to, today before you eat or as you are eating, you want to read and you'll find it. I know it's there. If I left it, then... Sorry? Okay, and then it's there. Who is the link? Who has found the link to the course? Okay. You ask, what's your name? Sorry? Please ask Philip where the link is, we'll show you. Are there any other questions? Yes. The quiz is in class, so it's in here. We shall come on a Thursday, and then we shall write an answer in here. Any other questions? All right, so if there are no questions, yes. Shh. Oh, yeah, it's online. It's here. It's in the. But I thought you said you know where the link is. The presentation is here. I don't know who has managed to access this yet. Yeah, I think I uploaded these last night or something when I got home. Are there any other questions? If there are no questions, guys, I'll see you day after tomorrow at 9, bright and early on time in NELT, right? 9 hours to 10, we have class. Thank you. Day after tomorrow, Saturday, 9 to 10. Thanks, I'll see you when you see me.